Did everybody find a seat? Good evening. Welcome. We'll let everyone settle in. We've still got a seat open there, one over there, a couple in the front row if you want to get up close for the Q&A. And then we'll get started. Huge welcome. Welcome back. Happy New Year. You're here, so that means that you have survived. You survived the craziness of the holidays, and you survived the craziness of the presidential inauguration. Yeah. Very proud to announce that the Silicon Valley Deep Learning Group is back. You're all here, you're back, you're stronger than ever, and in larger numbers than ever. The group is now 3,000 members strong. There's cake. There will be cupcakes. And because you are growing, this community is growing, and your needs are growing, the Silicon Valley Deep Learning Group is also growing, and we want to offer more programming for you. For that reason, we're becoming a nonprofit. If you as an individual would like to contribute in some way, or if you think that your company might be interested in being a sponsor or a partner, please reach out after the event to Adrian or Sophia, she's blonde in the back, or me after Q&A tonight. We're happy to talk with you and hear your thoughts. Or you can go to svdlg.com, that stands for Silicon Valley Deep Learning Group.com, and we'd love to hear from you. Speaking of sponsors, we'd like to share a gigantic thank you to NVIDIA for hosting us tonight, sponsoring, and for providing the fuel for our brains through dinner. And here from NVIDIA tonight to tell you about NVIDIA's Inception Program is the leader of that program, Arjun Dutt. Welcome, Arjun.
Thank you. I'm so clearly not the celebrity in the room. But I did want to say thank you for having your event here. We're so happy to sponsor this at such a great milestone. Congratulations on the 3,000 members. Just wanted to say thank you to everyone who made it here. This is obviously a super interesting topic. I have one slide that I'd just like to cover off, do a quick plug for the Inception Program. So for those of you who don't know and might be interested, so Inception is a new program. We launched it in the middle of last year, and it's focused on accelerating the AI ecosystem. As you know, NVIDIA, with our GPU offerings, we have a deep interest in seeing the AI ecosystem flourish. We're very interested in advancing deep learning. And so we've launched this program to help accelerate young artificial intelligence-focused companies. We've been pretty successful. It seems like there are a lot of AI startups. Since launch in June of last year, we are now up to about 1,600 applicants. It's a global program, so our membership spans not only North America, but also Europe and the Middle East, as well as Asia Pac. And it's a young program, and we're offering new benefits and capabilities for our members every single day. We help startups by, we're a hardware company, so we offer access to discounted hardware. We have a lot of in-house deep learning expertise, so we're able to help problem solve. We have skills programs, so to the extent that you have a data science team that wants to bone up on deep learning, we have the Deep Learning Institute that's available to help you do that. And for most young companies, at least the CEOs that I talk to, they're most interested in go-to-market help. And so we provide co-marketing. We have our own media channels and media outlets, so we'll blog about you. We'll feature you in a podcast. And ultimately, we also help make introductions if you're looking for venture funding, and most powerfully to clients who might actually buy your products and services. We'd love, if you have a startup or work for a startup, we'd love to see you apply. That's the little URL, and I'll chat with Rebecca and Sophia and team and see how we can distribute that URL later. And then we have our big GPU technology conference coming up in May, so just wanted to do a little plug for that as well. I did want to mention, for those of you who haven't noticed, we have cameras in the back of the room. We are recording the event, so I wanted to make sure you were aware of that. And I also wanted to say thank you so much for our friends from Understand.ai. They're visiting us from Germany this week. They're focused on applying machine learning and AI to creating ground truth data for automotive applications. So thank you so much for being here, and please do stop by their booth and check out what they're up to. With that, I just want to say thanks again for coming, and I'll hand it back to Rebecca to introduce George. Cheers.
Thanks, Arjun. Without further ado, introduce the folks we have speaking tonight. Our moderator this evening is Silicon Valley Deep Learning Group's own Adrian Kaehler. He's an entrepreneur, he's a roboticist, and he's also the author of Learning OpenCV3. And tonight he's speaking with our guest, who you might also know as GeoHot. He's the CEO of comma.ai. He's a hacker, he's a coder, and sometimes he's even a rapper. So please, please share a warm round of applause to welcome George Hotz.
Let's see if our mics are on. Testing? Can you hear me? Anybody hear any of this? Yeah. Okay.
I can talk real loud too.
So we're there's a little exposed here on these chairs, but we'll try to, not fall off if we laugh too hard at something. Well, George, thank you for coming out and joining us. We get together every month and talk deep learning and have different folks come represent different ideas and different thoughts, and founders and investors and people writing code and people pushing the field forward a little bit. You're sort of many of these things, so it's a real honor to have you here. Can you start off by just telling us a little about what's going on at Comma right now? It seems like the most topical thing and what everybody wants to hear.
So we're comma.ai. We're on track in 2 months to have the second largest network of self-driving cars in the world. Right now, Tesla has the largest, followed up by Google. But the thing about Google is their cars are actually owned by Google. Our cars are open source and available today. You go out, you buy a Honda Civic Touring or any Honda Civic with the Honda Sensing package. You can go online, download our plans for the Comma Neo, that's the hardware, OpenPilot, that's the software. Mount this in your car, plug it into the CAN bus, and it will drive your car for you. Asterisk in limited highway situations, very similar to what Tesla Autopilot 7 could do. So you can get Tesla Autopilot 7 right now on a $20,000 Honda Civic, and then you can build this for about $600.
Sounds good. So what do you need to do to set this up? So you need to get yourself this guy here.
Yep.
And is that a for sale as a whole object, or you assemble it? Or how does that work?
So comma.ai, we're big fans of free speech. So we only make plans, which are like speech, available on the internet for free. You can go, if you go to our GitHub, github.com/comma.ai, you can find the Neo repository, which has a PDF guide, which tells you everything you need to know in order to assemble one of these. Then you can go to the OpenPilot repository and install that on your Comma Neo, and that's actually the software, again, open source, you can edit it yourself, that actually drives your car.
So how do you see this going forward? So people are going to go and download this and build this kit and install it on their car. Where do you go from there? Where's that? What is that the doorway to?
We think of ourselves as the Android of self-driving cars. If Tesla is the iOS, where they have a closed ecosystem and they have, well, an autopilot, an autonomy system that is closed as well. You don't see Tesla licensing it to other people. You don't see Apple licensing iOS to other phone manufacturers. We think of ourselves like the Android, right? So we want to be available. Right now it's only Hondas, but through the grapevine I hear that people have it working on certain Chevys as well. You can put this on your own car and get something far better than what the manufacturer shipped to you. So where do we see this going forward? Well, we see people going out, making these, or buying it from one of the third-party, not associated with us, but we made the plans available for free. Of course, people are going to take it and they're going to, run with the idea. Maybe if you look, you can buy this kit fully assembled online. Download our software, put this in your car, and enjoy the second best autonomy system available to the people today.
So as an open source project, this project is largely involves deep learning, right? From things you've talked about I'll watch on YouTube and other videos you talked about. It's largely a learning system.
There's a deep learning component to it. So if you look at what Tesla Autopilot is, they have a Mobileye system. And Mobileye outputs the position of the lanes on the road, a prediction of the path, and the location of the cars. We've made a deep learning system that outputs exactly the same things, except, of course, ours is downloadable for free and runs on smartphones. Then we put all the other code around it, which is more similar to the autopilot code. When you know what path you should follow, how much should you turn the steering wheel to actually follow it? When you know how far away the car in front of you is and how fast it's going, how much should you hit the gas and brakes to drive appropriately? That's the big open source component of it. That's actually not the deep learning component, but all the image processing. If you're doing image processing without deep learning today, you're doing it wrong. It's kind of a scam. Or if it's not a scam, you need, look at deep Q learning, right? Wow, look, it learns to play Atari games. When you look at how much data it used to learn to play Atari games, it's absolutely astronomical. And that isn't just data. So you have to realize that the data we're getting back from the cars, we can't alter what the person did. It's not a simulator, right? So the technique that we use is a modification of behavioral cloning. Our network outputs the same thing the humans did. But the biggest assumption, I give this as an interview question, I don't know if I'll be able to give it as an interview question anymore, is the following, right? When you're training this net, your inputs are the pictures and your outputs are the path that the car should take, right? But at train time, there's no dependency from the output of the net back to the input. Regardless of what your net during training outputs, the next input will always be the same. This isn't true at test time, right? Because if you actually put this on a car, it tells the car to move a bit to the right. The next picture that it gets in is going to be more to the right as well. So dealing with that circular dependency is a very hard problem.
Have you investigated training it in a simulated mode, like some kind of video game kind of environment to train the network? And if so, any success?
Yeah, so not too much. We have a method now that works. In fact, the biggest thing holding us back now is not even our model learning abilities, it's our calibration abilities. Getting real-life cameras to behave, getting real-life smartphone cameras to all behave the same is real tricky. If you notice, Tesla's having the same problems with Autopilot V2 if you follow Elon on Twitter. But yeah, calibration is really tricky, and calibration has nothing really to do with the deep learning problem. But yeah, I mean, what's the question again?
The original question was about training the network and what parts of it were trained, and that's really what I was, a high level. So and then we kind of got into the details.
Sure. So good. What our network does, it goes from an image to a guess at the predicted path. You should drive the car this way. The location of the left lane or left barrier, right lane or right barrier, and lead car. Right? So you can kind of imagine it like you have a path and you have 3 barriers. Don't cross your left barrier, don't cross your right barrier, don't cross your front barrier. While doing that, try to follow this path. Works pretty well.
And when you trained this, how much data did you end up needing to train this system?
So we've gathered 760,000 miles of data now. This is data from the comma.0, which was the first car we built, the comma Neos that are out in the field, and the comma Neos in our fleet. Also our apps. So we have dash cam apps available for both Android and iOS that you can go download. They're linked from comma.ai. And for every minute of driving data that you collect with our apps, you earn 1 comma point. And comma points are great, and you definitely want to have a lot of comma points.
So are you getting a lot of success in that? I mean, sort of having the crowd come and help you and bring you data that you can use?
So we've got 760,000 miles. I would say that probably 20,000, maybe 30,000 are our internal miles. So the rest have all been crowdsourced.
In your vehicle internal data, do you also have the control signals or the state of the wheel and such, and then how do you kind of fill in that for the data that's on the end user app?
Visual odometry and the sensors in the phone. So we also log the gyroscope. We also log the GPS. So with a gyro, a GPS, and visual odometry, you can do a pretty good job at path reconstruction. If you want to label the lanes, we actually use old school CV. We use old school CV to label the lanes, though what we're moving to as of last week is a segnet. So we have an internal segnet that just basically segmentation network. If you've seen AI Motive has a really cool one of these. Basically, it's convnet, fully convolutional. You conv all the way down, and then you deconv all the way back up to the exact same size as your image. But instead of outputting the colors, you output the categories. And you put a softmax on each pixel, and then you can just backcrop that. There's been a bunch of cool papers on that. So we have one of those now that we're using to, basically, it's an automatic labeling system for the data that we have. We also have a LiDAR-based automatic labeling system, which we use to create the neural network-based automatic labeling system.
So for those of you at home, that was Vijay Badranariana's talk about 1 year ago. So if you were here, you long timers, or check it out on YouTube. So when did you sort of start thinking that deep learning was the way to go, like the way to actually address self-driving, or were you already playing with it for some other purpose, or what was your kind of history with deep learning?
I worked at Vicarious briefly. They're a AI startup out in the East Bay, and while I was there, I read all the papers, and I was super impressed with how far it's come since. I don't know. That was even the first I heard about ImageNet. I'm like, I always used to give people the troll computer vision problem, which is I give you an image. You output yes if there's a chair in the image, and no if there's no chair in the image. Figure out how to do this with more than 90% accuracy. And for years and years and years, no one could do this. Then 2012, AlexNet, and then obviously the nets that followed, you just saw a huge spike in accuracy. So the chair problem has, for the most part, been solved. Ilya Sutskever has a quote I really like. Everything humans can do unconsciously, deep learning can do. And that's true for the most part. Highway driving, humans do unconsciously. Deep learning can do it.
So how about the transition past highway driving? I mean, everybody must ask you this, but probably also your opinion on it changes as you evolve. Or what do you see from highway driving out to whatever you want to call it, like total?
My opinion on it doesn't change. I mean, so I don't talk about level 4. I don't talk about full self-driving. It's pretty much this, right? Like, think about what you can actually reasonably deploy in the next year. In order to get to true complete self-driving cars, you're going to need research, right? Like, those are not solved technical problems today. I don't believe that Google's approach of continuing to add huge list of rules is ever going to really work, right? So I think Google is, if you're being generous, 5,000 miles between disengagement events. Humans are 100,000 miles between disengagement events. So you still got 20x to go, right? Maybe it's doable. And maybe a company like Google can just throw so much engineering resources at it, right? Let's go back to the chair problem. Is it possible to solve that chair problem? The question, basically a binary classifier, is there a chair in the image, without deep learning? I don't know. Maybe if you threw enough resources at it, but it's certainly a lot easier to solve with deep learning. Now, as far as getting to that fully autonomous goes, show me something that can play Quake first. Once you show me something that can play a good game of Quake, I'll think that cars are just on the end of the horizon. But I haven't seen it yet.
Where do you put Quake compared to Go and StarCraft 2?
Well, so the thing about Go is, and I did see some of the new cool StarCraft stuff. So like maybe GTA. Maybe by the time they can play GTA, driving is close. Quake, you might.
Maybe that's not a good idea.
Quake, you might
testing your self-driving system with Grand Theft Auto.
Self-driving, Grand Theft Auto is the best, is the absolute best. Or maybe don't use their reward function.
Yeah, exactly.
Yeah. But yeah, you're still this like deep Q learning doesn't work, right? When you look at the huge amount of data, you kind of have like going straight from the pixels to control outputs. You're needing way too much data. You need sort of an intermediate representation. So one proposal, we wrote a paper about this last year that you can kind of think about is like, don't feed the pictures in. Train up a big GAN, right? Train up a GAN that is really good at reconstructing the pictures and goes down to like 1024 dimensional state space. The other trick is that state space should be Gaussian, right? Like you want that state space to be a Gaussian space. Then run your reinforcement learning, controls learning algorithms on that, and I think you will do so much better than what you've seen. Have people done this yet? The truth is, at comma.ai, what we're lacking is not the latest research. Like I said, the biggest performance bottleneck in this right now is the calibration of the cameras, which is what we're really putting our time into. But yeah, the truth is about a lot of these systems, like once you go from doing it on a simulator, where you don't have to calibrate a simulator, right? Your view is always the same. Maybe you have to deal with the 3 views that you can select in the video options in the menu, but like, then going to the real world where you don't just have to deal with this way, but you have rotation, you have all those other, I don't know if anyone's ever OpenCV, right? You calibrate the camera with all of those K parameters and those tangent parameters.
Targets, those checkerboards.
Models and field of view and checkerboards and asymmetric circles, right? So how do you do this without the checkerboards or the asymmetric circles, right? How do you do this from just driving data? And you can, but interesting problem.
All right. So I was asking you earlier about kind of your own boot up process. So you said you worked for this company and you just started reading papers. Was that
Yeah.
so you started reading papers and writing code, or what did you know, how did you kind of get from 0 to 60 for your own like personal process? I know a lot of people in the audience here are already experts, but a lot of people also themselves just starting, you know. So what do you, based on your own experience, what can you recommend, or what do you think is, or just what worked for you if you?
Jeff Hinton's course is pretty good. I did the Jeff Hinton course, and then take the state-of-the-art papers and try to implement them yourselves. Take the ones that have public data sets. Don't waste too much time with like, you know, like MNIST is cute to like learn the first things on, but don't waste your time typing MNIST examples. Take the latest, oh, it's a VAE GAN or something, and try to implement that. And you're going to struggle, and you're going to, you know, fail a lot at first, but then you start seeing about, you know, what fails and what succeeds. Also, don't just learn deep learning, learn actual machine learning, right? Like this is a field that has been around for a long time. People who come in say, oh, I know deep learning because I did the Jeff Hinton course, and to be honest, if you've implemented the good papers, you're probably pretty good. But don't discount all the previous research in machine learning. So actually, the way I really learned machine learning was before I worked at Vicarious, the Hutter Prize. The Hutter Prize, I really like this. Take the first 100 megabytes of Wikipedia and make the smallest self-extracting archive you can for it, right? And think about what that is. It's really saying, make the best language model you can. And then it's not just what's your predictive error, but it's also how small your model is, right? This is just like true, what's the, oh, there's the column graph complexity kind of stuff. But, you know, you take the length of the model plus the length of the data, and that's your true compression. So I tried to win this prize. And I spent months. I didn't win the prize, obviously, but I learned everything that made machine learning tricky, right? And the way I view deep learning is it is program search, right? Deep learning is search over a program space. I have a lot, at least supervised learning. I have tons of pairs, x comma y, right? Tons of them. The question is, find f such that f of x equals y. Now, you might think that this is an impossible problem if you look, oh, no free lunch, but no, right? Because there's structure to the data. The data is compressible, and because there's structure to the data, you know, you want to find, in some ways, the best compression of the data, right? The best, including the size of the model, so the model plus the data, right? Like, really look at it from that perspective. Don't look at it from, oh, here's a magic box, and here's the incantation I type into the API. You might be able to do this stuff in practice, but you'll never truly be great at it.
Did you find when you started that the tools were satisfactory? I mean, the toolkits that were out there, and then things have evolved, I guess, since that time. What do you think about the tools that are available and where the people are who are building all those tools? TensorFlow and whatever, Torch and everything else.
So when I started about the same time that Francois started writing Keras. Keras is phenomenal. Keras is so well thought out, and just that, like, you know, the fact that most of it was done in the beginning by one person with a very strong vision about what the API should be, it just was so much easier to use than like Theano and Lasagna and NoLearn and Torch and, well, I didn't know Lua, right? But
none of us did.
yeah. I mean, everyone learned Lua pretty much for this, but you know, and actually when I really learned Lua was when Karpathy came out with the char RNN stuff. If you guys, I tried applying the char RNN stuff to the Hutter Prize, and I thought I had something phenomenal, but what I did wrong was it was log base E bits and not log base 2 bits. Log base E bits are nats. I got scammed by nats. Yeah, I was like, wow, this error is lower than, I just need to put this and make this small. And I'm like, no, it's nats and not bits, right? So obviously you're off by a factor of change of base theorem, whatever.
So what excites you now when you look at the deep learning technology? Like, you look at things that are coming out, things people are doing. You mentioned a whole bunch of different things that went by pretty quick that probably some of the folks in the audience are familiar with, and others a little less so for some of the more contemporary ones. But what things, when you look at it, you just think, wow, this is so 2017, like it's great. You know, what excites you in the morning?
There's research and there's applications, right? So when you look at applications, and when you look at, truthfully, if you want the best like net to perform, look at Inception v3. Inception v3 didn't make great architectural or, you know, any sort of real improvements like that. What Google did was make a really big net and put a lot of data into it. And this is always going to be, you know, I read papers and they're like, look, we're using an L2 optimization, regularization norm. If I used a bigger net and more data and stochastic gradient descent, I'd beat you. So that's what it comes down to with applied. So as far as applied goes, I mean, Go was a phenomenal breakthrough, not because it was surprising. Like, I wasn't surprised at all by Go. Like, there were a few papers where they were showing COM nets to predict a Go state. The first person who manages to stick COM nets to predict the next move in Go with Monte Carlo tree search is going to solve Go. And of course, this is what AlphaGo was. So that's kind of the practical. Inception v3 maybe in 2015 and Go in 2016. The research, batch normalization, that was a pretty cool breakthrough. GANs, the story of 2016's GANs are really cool. GANs are really cool because the first thing that people are like, you want to train a autoencoder for an image. Mean squared error is a terrible loss function for images. It's going to throw away all your high frequency information, right? But if you use a GAN, you're actually training, in some ways, the loss function when you train the discriminator, right? So your loss function is actually encodes, well, the same sort of structure in the net that your comms themselves encode, right? If something is good at classifying, it's probably also good at discriminating, right? It's just the whole trick with GANs. The thing that I'm most excited for, and something I've been talking about since 2015, and people are finally seeming to, okay, so deep learning, when you're doing the optimization, you're doing program search. You're searching for the best possible program, right? But why keep this only at the object level? What if you started doing this at the meta level, right? Instead of using this fixed optimization function, what if you use a learned optimization function? So by the way, if you want to know what the next thing in deep learning is going to be, just look at Jürgen Schmidhuber's papers 20 years ago. Read them and be like, they're going to rediscover that 20 years later, give the man no credit for it, but make it really good. No, I mean, that's kind of that. But yeah, so I think you're going to start to see this stuff take off. The other stuff is, I think you're going to see a breakthrough in 2017 is long distance temporal learning, right? So right now, maybe you can backprop 10 with an RNN, 100 with an LSTM. But how do we get contextual windows back to 1,000 and 10,000, right? So right now, if you're using backpropagation through time, what do? You go to 50? You get 20, you go to 50. Maybe if you really want that, you go to 100, but it probably doesn't work that well, right? How do you get longer term temporal dependencies? My prediction is this is going to be some kind of like tree structure, right? And you have like skip nodes, or maybe like kind of a ResNet thing on the RNNs, right? Like ResNet through the RNN layer. I don't know, just like this.
When you're for comma.ai, presumably you're always kind of looking around and seeing what people are doing. What's the hottest thing? If there's anything new that's going to be useful to you in particular, right? Is there things that you see that are maybe more specifically important to your context or to the context of driving that are interesting to you that you see emerging as you kind of keep your eyes on the horizon?
So we had a phenomenal intern last summer who was the first author on our paper. The idea was basically this, right? So there's this problem with behavioral cloning, right? I usually use a whiteboard for this, but if you think like, if a car is in the left part of a lane, it's not going to want to go back to the center if you trained it with behavioral cloning, because what is most likely to have occurred previously in the data when it sees a car on the left side of the lane is it's going to continue on the left side of the lane going straight. That's what the recovery motion is very rare in your data, right? And because there's no sort of reward function, there's no way to penalize the car for not being in the center of the lane. This is why we still do this with old school stuff. You'll actually read the penalty function for not being in the center in OpenPilot as in the Python. It's not in the deep learning. There's other ways to get around this too. NVIDIA uses a trick with 3 cameras that's cute. And then their paper, it's cute. You got to have 3 cameras to train on. But so our idea was this. Let's decouple the learning of a policy from the learning of a world model, right? Can we use our massive amount of data about the world to learn a world model? So you can think of a world model as a function of the state at time t and the action at time t equals the state at time t plus 1, right? That's a world model. So you can learn one of those. You can learn one of those today. Even if all you're learning is state at time t to state at time t plus 1, you can learn this today with a GAN. To some extent, and you have the temporal context problem again, which is why we didn't push on it too far. But once you've learned a world model, you can then effectively do RL in your world model. And you don't have to do RL on pixels. You can do RL in your learned GAN space, like I was talking about before, right? If you have like a state vector in the middle of your GAN, you can RL on that. It's A, much lower dimensional, if you count each pixel as a dimension, and B, much more regularized. It's probably Gaussian, right? If you use like batch norm all the way down, you're probably going to get a Gaussian space in there. Actually, I think with GANs, you even have to get a Gaussian space because your randomness generator is Gaussian too. When you're randomly generating, well, okay, you don't have to do this, but if instead of an encoder network, you're using just like you randomly generate for the decode. Actually, I think that's what most GANs are. Then if your randomness source is Gaussian, you're going to end up with a net that goes to Gaussians.
So let's see. What is it? I just had a question on the top of my head, and I've forgotten it. So
It was
when you're
all off
talking
my
about open source, right? You mentioned something that just caught my ear. You said it's in the Python, not in the deep learning. When open source code, in the days before deep learning, right? If I open source the code, then you really kind of have the code, right? I give you the code, you have the code, you can run it, it's all good. But if I'm open sourcing deep learning code, then in some way I'm not really giving you very much, because unless I'm open sourcing the data, right? And then there's some intermediate state where maybe the weights, of course, are available, and so in some sense you have something you can execute, but you still may not have any idea how to reproduce them. So there's two questions I have on that. One is how do you think about the open sourcing of data if data is the thing, which is really the reference point for the, if you like, the intellectual property. And then on the other side, what does it mean? I mean, the open source community, one of the great powers of open source in the last few decades has been so many eyes on any piece of software, right? So if you wonder, well, gee, can I rely on the Linux kernel or whatever? One of the things that you know is that many, many people, probably many of them smarter than oneself, have looked at so many parts of it, and it's had so many chances to be debugged and understood. But in the deep learning case, how do I get that benefit? Or is there some benefit like that in the deep learning environment?
So first off, when you look at the Linux kernel, it's a myth that most contributors to the Linux kernel are independent individuals. They're not. The biggest contributors to the Linux kernel are, I think, IBM, Google, Red Hat. Oracle never gives you any code. I'm sure Canonical contributes some back. All the driver vendors are giving you some back. Android's probably even managing to upstream some poor quality code into the kernel. But, oh, yeah, this is Android, right? The operating system that runs on here, also open source, called NeoS. It's a fork of Android. Android is terrible. Compared to iOS, iOS is beautiful. But yeah, so how I think about the difference between, well, first off, comma.ai does not open source this because we're altruistic. Comma.ai open sources this because, well, a few reasons. One, if something is driving your car, you should know what it is, right? Like the thing that's actually outputting the signals, that's controlling the 2,500-pound box around you, you should kind of know what it is. It's also to deal with the issue that comma.ai has, which is lots of people have lots of different cars. We would love to support all of them, but we don't have the resources to do it. So by open sourcing it, if you want it to work with your car, you can do it yourself, right? Now, with deep learning, the thing is, if you open sourced everything needed to reproduce the weights of the model, which would be the code and the data, you're in some ways not just giving away the code, you're also giving away the process that created the code, right? So when Google open sources TensorFlow, they open source a piece of code. They don't open source, well, here's all of our team communications, and here's all of our internal Google tools we're using to debug TensorFlow. And by the way, here's also access to our large clusters of Borg machines, so you can run these tests yourself, right? So there is kind of a difference there. But yeah, I mean, I don't know. I'm not sure. And it's going to be interesting to see like where the value shapes up in the future. The other issue is just a practical issue. The Linux kernel is like 80 megs. The data set that we use to train this is 100 terabytes. If we open sourced it, what would that even look like? How do you open source 100 terabytes? You need to buy a $5,000 machine just to hold that. Maybe a $10,000 machine, right? So that's kind of the issue there. Now, this, of course, will change as Moore's law continues to Moore's law, as it does. to the point that it's like, oh yeah, no, I got a 100 terabyte flash drive right here. You can buy these in Shenzhen. And they'll show up.
But by then you'll have a 50 petabyte data set to train your network
Well, exactly.
on. I mean,
Yeah.
is deep learning killing open source, right? I mean, is there going to be a time when everything that's worth talking about is a trained network and nobody can, whoever has the data, everybody's open source the code that trained it, but all the data sets are essentially private and immobile? I mean, are we sort of headed back to the 70s?
Cory Doctorow said 10 years ago that general purpose computing was going to die. Seems good and alive to me, right? I think that all things like this are kind of too soon to think about. I think that right now, it's amazing how open. It is amazing how open these companies are being with all of their research and all of their code. Imagine Google kept their deep learning research to themselves and kept TensorFlow to themselves. It is amazing that they are doing this. Now, there are, of course, strategic reasons they're doing this. Maybe they're preparing for the world where the value is all in the data and the network. But it'll be interesting to see how it plays out. We have the same position as Google, whatever Google does. If Google open sources their data, we'll open source our data.
Well, about a year ago, I was at a talk, and Andrew Ng, who probably most of us know, he very specifically made the observation that, you know, intellectual property as we understand it in software is changing in a very fundamental way, and that the defensible boundary, as he called it, is now the data and not really the code. So I was just wondering about your thoughts on what that means for open source, and how does one, if you're interested in creating the benefits of the open source community and seeing that continue into the deep learning era, like what are the things that you think play a role in really empowering that, or helping the open source dynamics play a role in the world of trained networks and data?
Well, we're already seeing it, right? I mean, we're already seeing the fact that TensorFlow is open source, right? And this is kind of a break from historical Google, right? MapReduce is not open source. The old thing they had before TensorFlow wasn't open source. It's amazing, and we should all be, real grateful that they decided to open source that for us, right? Because the alternative is Theano. Have you guys ever read the Theano code? I mean, Theano is fast, but it manipulates large strings and concatenates them together in huge messes of Python. Read the TensorFlow code; it's nice. Like they really thought out everything, and it's going to scale to the future. So I don't know. I mean, it's interesting, to sort of say what the benefits of deep learning were in the first place. Maybe the replacement for a lot of eyeballs looking at the code is a lot of people contributing data, right? I mean, if a lot of people are contributing data to this net, I mean, so one of the coolest things about the comma.ai driving data set is its immense diversity, right? Like, you think about the data sets that have existed before for driving. Google's data set is collected on all the same model car, with all the cameras in the same place, with all probably the same sensor of the cameras, the same noise characteristics, same thing with Tesla. We got this data set from phones, right? And it's amazing how, if you really want your nets to be robust and reliable, you use data augmentation, right? But wouldn't it be even cooler if you could just have your data kind of pre-augmented? We have all of these interesting noise models. If some sensors are broken in weird sort of ways, we're going to find them. I guess Tesla would find them too. Google won't. But yeah.
So what do you think about introspection with deep networks? So, if somebody's going to buy this device and put it in their car, and I don't know if you all had this experience, but there's a moment when you're in a self-driving car when something happens, like a bunch of mud splashes up on the windshield or something, and suddenly you know that you can't take it over, and so the car's really going to drive, and you'll survive, or it'll kill you. I've had this experience. So when you have this thing here, it's taking over your car and driving along. Now, of course, you could grab the steering wheel or whatever, but you're trusting this thing a lot, right? And so if it was sort of open source code of the more traditional kind, if you were a bit paranoid, or maybe just sensible, you might go in and really look through that code and think, hey, is this reasonably bug-free, or whatever you want to do to introspect into it, try to understand that code and what it's going to do. With the deep network, how do people trust it, and how do people look at this giant pile of weights and say,
statistics? This net has driven 10 billion miles. It's never crashed. That beats all people.
Is there such a net?
Not yet. But I mean,
how do you know you're not the weird one? How do you know that your case isn't unusual?
You can't think about it like that, right? You're always the mean. Rationality 101. Unless you have some evidence to say otherwise, then go ahead and use your Bayes rule. But No, it's like, how do I know how good of a driver something is? Statistics. How long has it driven for? And you have to watch out for one more assumption in machine learning. You're always making the assumption that the previous data is, in some ways, the same as the data or indistinguishable from the data that you're currently on right now, right? So if some net has driven a car for 10 billion miles on the exact same highway system at the exact same times of day that I'm in it right now, I'd take a nap in the back seat. I'd trust it with my life. Now, everything we do is level 2, and you should pay attention at all times, and nobody, not even Google, is anywhere near where you can take a nap in the backseat safely, right? So it's important, if you do see these systems in the real world today, do not trust them to drive a car, even when they look like, from your perspective, that, wow, this thing's driven the car for like 50 miles and it hasn't crashed. I'm going to take a nap. 50 miles is not statistically significant. But once you get into these statistically significant numbers, so humans, you have a fatality in a car once every 100 million miles for humans. If you show me a net that's driven 1 billion miles and hasn't crashed, again, making the train test assumption, yeah, it's 10x safer than people. When you get in an Uber, do you look inside the Uber driver's head? Do you look inside his head, make sure the weights of his net are all aligned right?
No, we have other people's little star ratings.
Oh, we have a little star. You know what? We'll give the net a star rating, too. 1 star. Drove my car into a ditch. My wife and I were stranded there for 3 hours. Would not drive again. Right? Give feedback.
So how far are you from having that kind? I mean, how that kind of mileage, even that kind of mileage in the data set? You mentioned earlier the size of the current data. How fast are you accumulating data? And when do you imagine that there'll even be enough data to make, I mean, assuming the network is working that well, but to be able to make those kind of statistical statements?
Tesla is getting close, right? Now, Tesla's network, of course, if you've been in a car with autopilot and you drive it from Mountain View to San Francisco, I think you'll probably have on average maybe 2 disengagements. If you're doing that on average, it's kind of similar to ours. I mean, if 2 disengagements on a 60-mile road, you're like 20 miles between disengagements. You're not even close. But Tesla does have about the scale required to make the safety judgments on the cars, right? Like, they're deploying a net to cars that are going to drive like 1 billion miles, say every, what is it, like 1 billion miles every year or something? So within a year, if they had deployed a net and there wasn't a single disengagement event for the year, then, yeah, Tesla has kind of the resources to prove that. You probably don't even need 1 billion. You could probably do it with less. I don't know. I mean, do your statistics right. But 1 billion is just a number that I know right away that I would trust because I know how safe people are. So Google has hundreds of cars in their fleet. They don't rack up miles that fast. I think Google just crossed the 2 million mile mark. 2 million miles, and like I said, we're only at 760,000, so I'm not saying we're there either, is nothing and proves nothing. Maybe you can show some things. I think humans get into car accidents maybe every 100,000 miles. So you might be able to say something, but it says nothing about what's going to happen sort of in like a fatality case, right? So when are we going to be there? I don't know. How fast are you all going to build Neos? Build Neos, put them in your car, download our dashcam apps, help us out. Let's get the data there.
Sounds good. Okay, well, we want to have a little bit of time for folks to ask questions from the audience. So, as we always do, it's kind of our format. I don't know, Rebecca, do you have a walkabout mic or somebody have a walkabout would like to take questions? And presume for George, you can ask them to me if you like, but George is more interesting, and I'm here every month.
And if you could also say your name, and if you want to name a company you're with or any affiliations, feel free.
Deval Brambat, 5-Chip Corporation. My question is that of hardware. I'm not sure if that simple gadget you're holding will provide enough sensing for the car to self-drive. Could you please respond?
Sure. So we're not just using the sensors that are on this device. This also connects with the CAN bus of the car, and the cars that we support also have radar sensors. So we're using the radar sensor from the car, in addition to all the other sensors on the car, right? So each wheel has a different speed sensor, the steering wheel has a steering angle sensor. So we're using all those sensors as well. You can check out, if you go to the Open Pilot project, click on DBCs. DBC is like the car interchange format. You can see all the sensors that we're getting off the car. So we're also using the camera from the phone. So we use a camera plus a radar, a single forward-facing camera plus a radar, and that's the exact same thing as Tesla's V1 autopilot hardware. And our camera is significantly better than their V1 camera. Their V1 camera was a monochrome, lower dynamic range. This is a high-end 16-megapixel cell phone camera sensor. So our hardware is on par with autopilot V1. Is it going to drive your car level 4? No, of course not. Is it going to drive your car pretty nicely up the highway? Yeah.
Yes, Misha Orel, F1 Genomics. I had to change my question because the previous guy actually asked pretty much the same question. So what I want to ask, what kind of radar they have? Is it like scanning radar, or it's like one direction, just forward-looking radar? Is it LiDAR, or it's radio?
It's radar. And actually, I'll add one thing to the sensor question, since you're interested in it too.
Yeah.
So a sensor that we're going to start rolling out, a sensor that a lot of people don't think is really a sensor, but map. Map is a sensor. Like if you have a very accurate map of the world and you can localize yourself on it, that gives you information about the world. If the road's going that way, you're going that way too, unless something majorly changed on the road. So it gives you information. Obviously, no sensor is perfectly reliable. People are always like, but what if the map changes? No sensor is perfectly reliable. You have to deal with that statistically, right? So coming back to what radars are on cars. So the radars, they're radars. They use radio waves. Most cars are 76 gigahertz. It uses basically a sawtooth wave. It scans through like 74 up to like 77 gigahertz. And then it uses a phased array antenna to make the beam go like this. So you get maybe, now the one on the Honda is not that great. You only get about a 45-degree arc. We have a much better one by Delphi that we use sometime. You get about 90 degrees. And radars are very accurate. They're very accurate at giving you the speed. They're super accurate at giving you the speed because you can use the Doppler effect, right? Like LiDAR can't, LiDAR's not even the Doppler effect. So LiDAR's not that good at speed. I think radar is in a lot of ways better than LiDAR. But yeah, they're not that precise spatial resolution-wise. They're pretty good at distance because distance you can do with timing. And then you can do the phased wave too, which is real accurate. But they're not very good at like, where is this? And the automotive ones are terrible at this axis. And this is why the Tesla truck accident happened, right? So the radar can't tell the difference between a sign or a manhole cover versus a car, an object in your path, because they have a pretty wide beam in this direction. I mean, it starts out kind of narrow, but you know, it spreads out as you go. So yeah, radars are terrible at that direction. But you can build better radars, and we can talk about how doable that is. Also, the software on a lot of these radars is pretty terrible. They put these like small DSPs and these like low-quality Kalman filters. You throw deep learning on raw radar data, you'll do so much better than what they're doing right now.
So why don't you use two cameras, like binocular cameras?
Because cell phones have one.
Oh, okay.
Yeah, I mean, so another thing about stereo, right? Like, so you think you have two cameras, right? So you can get depth information from that. But I already have two cameras. I have this camera here, and then 50 milliseconds later, when I take the next picture, I have this camera over here.
Oh yeah,
right?
Yeah.
So it's effectively the same thing, and you can use the same sort of algorithms to recover depth. Usually when it's used like this, it's called structure for motion.
Hi, Matsu. Do you have a sense on how the auto and self-driving car industry is going to handle the ethical issues of whether you crash this way or that way or something like that?
100 people die a day in car crashes. Those car crashes are not because they can't decide whether they want to kill the mom or the two kids. They're because people are drunk, distracted, or asleep. And I think that whenever that's brought up, it's a major distraction that's actually causing literally 100 people die a day in car crashes.
Sure, but we'll need eventually to make decisions.
No, we won't. It's really not a big deal. It's really, the trolley problem is so overhyped. The official comma.ai policy is computers don't make ethical decisions, so we disengage and give control back to you.
You have any other questions?
I have a bit more technical. My name is Scott. First of all, the model...
I'll wait for the mic, because then it'll end up in the recording for our viewers at
We'll make
home.
our way around the room this way after you.
So first I want to know what's the size of the model that you actually trained? Like, can you give a bit, I guess, some kind of CNN and RNN of some LSTM or something? So that's one thing. And what do you think about fine-tuning the network, giving the user at the end? I guess you don't want each car to drive differently, of course, but maybe some fine-tuning while you're not getting too far away from your original solution.
So, okay, to answer the first question, the model is 5 megabytes. It has about 1.2 million weights. We could easily go down to FP16 and lose almost nothing, but I'm just lazy. Our model runs at about 25 milliseconds, and we have a 50 millisecond frame time, so we already have plenty of overhead, but we could certainly go down to like FP15. A little bit about the architecture. It's a CNN piped into an RNN. Sometimes I troll people and say the RNN goes first, but if you're putting an RNN on all the pixels of the image, I don't know what you're doing. So yeah, it's a CNN, goes down to an RNN. It's not even an LSTM, it's an RNN. We use it almost like a Kalman filter, kind of for smoothing. The problem with LSTMs is they lag. In most applications, you don't care. You do it in speech track, you do it in machine translation, you don't care if it lags. But you want to do something in actual real time. Suddenly you're getting 250 milliseconds of lag, and it's real bad. So what was your other thing?
My second, talk about fine-tuning.
Oh, fine-tuning. So yeah, you absolutely do not want to do training on the device for a few reasons. One, it's very hard to verify anything once you start doing that, right? So right now, we at least have a validation set that we run our models through, right? We could say something about, the validation set's not perfect. Ideally, what you want to do is test in a simulator, but at least it tells you something. The second you start training, you've lost all ability to validate. And yeah, so fine-tuning is good while you're still here, but as far as actually training the models on the device, also training is very power-intensive. You're going to need, it's just well beyond the compute resources. You're much better off with any gains you would get from fine-tuning, you are much better off training a larger network back at your place and then running it on that GPU.
Here you go.
North.
Here you go.
Oh, sorry. I guess. Hang on. There's one more over here.
Excuse me. How your design or bugs predict or prevent the car accident? Predict and prevent from the car accident.
How do we predict and prevent car accidents? Well, so all of the data that's been uploaded to us, we haven't looked that carefully. There may be a few car accidents in the data set that we're actually training on, but it doesn't matter because statistically. So here's the thing. Talking about car accidents, you can also kind of talk about the bad driver problem. And I think it's an Anna Karenina quote. All good drivers are good in the same way. All bad drivers are bad in different ways. I think they say it about families. But no, it's true because when you're training these models, the bad kind of all averages out in the noise because they're not all bad in the same way, while the good is a big peak in the signal, right? So don't think of this thing like the average driver. Think of it like the committee driver. Imagine you had 100 people sitting in a room and all voting 100 times a second on what the car should do. I would trust that committee car a whole lot more than I would trust any one of those individuals even driving the car. Now, I would not trust the average of them. We'd crash pretty fast. You guys remember Twitch plays Pokemon, right? But yeah, so how do you prevent car accidents? Well, there aren't many car accidents in the data set. And if you make the train test assumption, well, people didn't crash the car when they were training it, so it's probably not going to crash when it tests. How do we prevent them perfectly? So we're not level 4. We are very much level 2. Our safety assumptions that we make always involve the human paying attention at all times. When you turn this on, it comes up with a big warning, always pay attention. The same thing as Tesla Autopilot. These are not, you can take your attention off the road, but these are, I'm not saying take your hands off the wheel, but the wheel's going to turn for you. So, yeah.
Hang on. There's someone in the back. Wait for Rebecca to come by with the mic. Okay. Yeah, Rebecca?
I am Paulo. I have a strange question. So you were saying if you take Uber, you don't look in the brain of the person that is driving. But actually what we know for sure is that the guy, on average, if he's a normal human being, he fears to die. So he will not do anything crazy to risk his life. Do you see, in terms of technology, do you see anything on the horizon or any possible technological approach that would give a kind of barrier to the machine, to kind of a fearing?
Yeah, but you don't even have to think about it that way. Fear, that doesn't even so you don't trust the Uber driver. Okay, maybe as a human, humans are really irrational. From a rationality perspective, you may be like, No, from an irrational human emotion perspective, you may model the other driver and kind of think, well, I know I'd be afraid to drive if I was driving a car, so he's probably afraid to die too, and therefore he's not going to crash. But the truth is, if you're looking at this rationally, which whenever you're thinking about, big picture things like car accidents, you should, the only thing that matters is the statistics, right? And funny enough that the star rating was brought up. In some ways, that's again, it's a statistic, right? You're gathering this aggregate data about how this driver or driving agent, don't discriminate, performs, right? It doesn't matter if the net is afraid to die or not. The only thing I care about is statistically, wow, this thing drove 10 billion miles and didn't crash a car. I trust it, right? I don't care about the net's motivations, right? Like, I don't care about the motivations. I only care about the results. And the results are superhuman if you're at 10 billion by far.
Hi. So you talked about the state Google and Tesla are in. Would you like to comment on how Uber is doing and what you think about them?
I like Uber. I like Otto. I like Anthony Lewandowski. I think if anyone's going to single-handedly play a major role in ushering in self-driving cars, that guy. But yeah, I mean, Uber, something Google really lacks is the aggressiveness. If Google was more aggressive with like a go-to-market, let's build 10,000 of these things, let's get them all over the city of Mountain View, let's force our way through the political process like Uber does, Google could have been the majorly dominant player in self-driving cars. Again, it's looking like they're going to be the Xerox PARC. It's just true. Really cool stuff at Xerox PARC, but so Uber, like technology-wise, I don't know, they're probably about on par with cruise automation. There is kind of a business challenge for Uber, which is Uber makes no money and saves no money until they can actually remove the driver from the driver's seat. In fact, if you have a safety driver there supervising the network, you probably have to pay him more because he has the name safety in his title, right? So the truth is Uber loses money, and it is a major money sink. In fact, all of Uber is a major money sink. So if Uber for the next 5 years can continue to find investors to pour money into them, I see the potential for one of the biggest payouts in history, right? If the second Uber gets, it isn't just a question of solving self-driving, it isn't just a question of building a level 4 self-driving car. It's statistically validating it and then somehow convincing politicians that statistics are good. You got to do both those things. But the day you can do that, you buy a car company, and literally those cars will drive themselves off of the assembly line and start making you money, right? Which is, when you think about that, it's an entirely automated assembly line that builds self-driving cars that then drive themselves out of the assembly line and start bringing in money for the parent company. Wow. But yeah, so I see Uber as a great target to be acquired for $2 billion in, say, 2 years. For comma.ai to be acquired. So.
Okay, let's take one more question. There's a gentleman here who's been waiting for the mic to make it slow, counterclockwise arc to him.
Hi, my name is Ashok. I see the current supervised learning techniques. I can't see how they can scale to the level 3 and the level 4 systems of autonomy. Do you have any ideas on how machine learning can actually make it happen?
Yeah. So I agree with, do you work at Tesla?
I do.
Okay, cool. Yeah, I agree with you that it's going to be hard to take like these current, like our current methodology is not going to scale anywhere past kind of level 2 in ADAS. So you're going to have to do a few things. So you can really divide driving into several problems. There's a perception problem. There's a localization problem, which you can kind of think of similar to perception, but perception, localization, planning, and controls. Out of those 4, controls is easy. Controls is literally, if you read the paper and do a good job building the thing, basically saying this is the path I want the car to take. To actually get the car to take that path is an easy and well understood problem. I would say probably after that, localization. Localization can be solved. So Google solves localization incredibly well. Tesla probably is building one of these too. We're certainly building one of these, which is a massive map, basically, a massive high definition map that can localize you anywhere. Localization is already solvable if you throw enough money at the problem. Google uses a LiDAR. They can localize to like 2 centimeters of accuracy anywhere in their pre-mapped region. Localization is already solved. Perception is what we're starting to see fall with things like segmentation nets and depth nets. A lot of, it's really, and it's NVIDIA chips that are going to be powering all of this stuff. You put a bunch of cameras on the car. You're saying these pixels represent a car. These pixels represent a road. These pixels represent a lane line. Then you're left with this big scary box in the middle called planning. So I think, I might be wrong on this, but I think almost all of Google's disengagements are planning failures. Google's bus accident was certainly a planning failure. It's not that it didn't see the bus. It's not that it wasn't localized perfectly. It's not that it told the car to brake and the car didn't brake. It was that it made a bad plan. The techniques to solve planning don't quite exist yet. So right now we have a very simple, and you're going to start to see in OpenPilot. We're actually right now refactoring controls out to controls in Planner D. Planner D right now is very simple and just kind of uses the output of these neural nets. But this is what's going to get better. Like I said, yeah, it's like, look at what we did in our paper. GANs, processing the image down to smaller feature spaces, maybe even putting some loss function in the reconstruction, which says, look, I don't care about the sky and the trees. Then doing some sort of path planning on that produced vector space using some deep learning trick. And I think that's how you're going to get to level 3 and level 4. But we'll see.
All right.
I like that question.
Yeah. Shall we wrap up here? Oh, okay, but make it short.
All right. In driving, it's all about the corner cases, right? It's not the average case that's hard. It's the corner case where it's raining and there's some oil on the road. How can we get data for that, right?
Well, the truth is, if data is big enough, there's no such thing as a corner case. So I don't know what it is that make people, for some reason, trust the big mess of if statements way more than deep learning. The big mess of if statements is incredibly nonlinear. When you think about the nonlinearity of an if statement, right? Like really think about it. Compared to something like an LU, which is a beautiful, beautiful unit. Look at that. It's so smooth. Look at that smoothness of the LU, right? Like it's not linear, but it's kind of close to linear everywhere I look. The if statement is nowhere close to linear, right? So if data gets big enough, there is no such thing as a corner case. The truth is, there are going to be some true corner cases, and we're going to have some accidents. But again, anyone who's thinking that self-driving cars are going to get you to 0 accidents, I mean, maybe someday magically. But today, I'll certainly take something that's twice as safe as a human, right? So there always are going to be corner cases, but there are corner cases for humans, too. The question is getting data sets large enough such that these corner cases, right, like someone cutting in front of you on the highway, that's not a corner case. We've seen that thousands of times in our data. These really, really weird edge corner cases, that's where humans crash too, right? It's not about building a perfect driving system. This isn't a game like checkers that you can solve perfectly. This is a, let's build something better than what we already have. So, yeah.
Thanks.
Okay, everybody, let's thank George for coming out and talking with us tonight. And we still have access to the space for almost another hour. This is a great chance to get to know folks around you and say hello and make some new friends. And I think there might even be wine somewhere and maybe even some leftover pizza. So thank you, everyone. Thank you very much. Thank you. Thanks, George. This is really awesome. Thanks for coming out.